Hello, everybody, and thank you so much for joining us for our penultimate installment of the Fall 2021 Closer Look Journal Club. I'm joined here today by my colleagues Manuel Rausch, Matthew Bercy, Johannes Weikenmeier, and Adrian Buganza-Tepole. And today we are thrilled to host Kevin Moerman. Dr. Moerman is a lecturer in biomedical engineering at the National University of Ireland, Galway, and a research affiliate at the MIT Media Lab. Dr. Moerman has many active research interests. Notably, he's done significant work in multiple aspects of computational biomechanics, ranging from developing meshing tools to developing image segmentation pipelines to performing finite element analysis. And what's really cool is that in addition to all of this, he's also a serious advocate for open science, and he maintains the open source project GIBBON, which he'll talk about today in conjunction with his recent paper on automated and data-driven computational design of patient-specific biomechanical interfaces. Dr. Moerman, please go ahead. I'm really excited for your talk.
All right, thanks a lot for the introduction. Once again, the audio is okay, right? Just let me know if it's not. All right, so let me describe the problem. I'm going to talk about biomechanical interfaces. And so one problem is that, well, many people suffer from limb loss. In the USA, for instance, more than 500,000 people, but worldwide it's a big problem. One amputation is carried out every 30 seconds globally. And several advanced prosthetic devices have been proposed. You can see here this video, this TED Talk that was given. It was a specialized prosthetic device for dancing. The latest TED Talks from the group here at MIT, or there at MIT when I was there, feature climbing prostheses. So there's very fancy prosthetic devices being created. They're just very expensive, I suppose. And a critical aspect still, can you see my cursor? Can somebody confirm that? Can you see the cursor move or not?
Yes.
Okay. So here you can see the socket. That's a prosthetic socket. That's an interface to the human body. So I think that very advanced prosthetic devices have been created underneath that. But when it comes to the connection to the human body, things are still complicated. We have to switch from an engineering device to soft tissue of the human body, and that can be very difficult. So 60% still experience moderate to severe pain in walking in a prosthetic socket. And you can see from this picture that the bones tend to end abruptly after amputation, obviously, right? So it's a downwards pointing sharp tip with very little soft tissue underneath. It would be like walking on your tippy toes the whole day, right? So what the difficulty here is designing a shoe that allows you to comfortably walk on your tippy toes all day. That's kind of what you can imagine. And tissue damage and pressure ulcers remain common. But this is really critical. This socket, this interface, you can make a very fancy robotic actuated foot ankle system, but it'll fail if the connection to the human body, the socket, will not work. So this is an open problem. And the current state of the art here is to use a manual process. So very highly skilled prosthetists tend to do this by hand. So they create a cast of the leg, say with plaster, and then they create a mold of that, a counter mold, and then they wrap carbon around that, which is a very rigid socket, then I suppose, right? Very hard and stiff. And that'll form the mold for the socket. Now they do adjust it. So you can see here where my cursor is, there's sort of an indent. Oops, sorry, there, oh no, going ahead. There's an indent there at the patella tendon, just under the kneecap, where it's quite safe to load, so they push a bit harder. At the calf, they change the shape inwards a little bit as well, but they try to stay away from vulnerable areas. And this is really, you have to be highly skilled to be able to do this. And it's not so repeatable. So different prosthetists do it differently. And if you ask them to do it twice, it'll be slightly different again. And the sockets are currently mostly rigid and commercial liners. So one size fits all liners are used. What are liners? They're kind of like a rubber sock that is put on, which forms a layer between the skin and this very rigid socket to make it a bit more comfortable. Often it's sort of a soft silicon-like sock. So these frameworks, or this is not a framework, I suppose, but these methods are insufficiently data-driven, in my opinion. And they're not repeatable. So the current state of the art tends to be rubber socks and wooden clogs. If you think about your own feet, right, that would not be comfortable. The socks, those rubber liners, are not so breathable as they should be, and the sockets are rigid. We can make changes there, and the design is not repeatable, not entirely scientific and repeatable in that sense, and it could be much more data-driven. So can we come up with a framework that is much more data-driven and maybe even fully automatic? So that was my job when I joined MIT as a postdoc initially, and then a research scientist, and now I'm at NUIG in Ireland. But when I worked there, I worked on, so here A is an MRI scan. So we take an MRI of someone's leg, and we can segment the geometry. So we have the shapes. So that's B, surface shapes. Then we could do an indentation test on their leg because we need to inform a mechanical model and have the correct constitutive properties. So we do inverse FEA. Then we would like to automate the design process. So that's E here. And then we need to know how well it, how to fit it. So it needs to change shape and fit around the limb in different ways, right? So say a bit harder at the calf, a bit less at the shin bone. And that's a design problem that we have to solve. And then we need to optimize that design and evaluate it, see if there's high pressures on the soft tissue or high strains in the soft tissue. And then we move to 3D printing. You export the files, you print it, and you give it to the subject. Now, this should ideally be the same design every time, right? Highly repeatable, everything depends on data and science, and that's where we want to go. And all the tools that I'm presenting have been created using GIBBON, which is my open source toolbox. Now, I want you to test it, but I would also love it if you join the project. So I'm looking for more people to test it, say, within their PhD project, and to maybe contribute some code back to the project. So if you're interested, contact me afterwards. So let me go through these steps of the process. So step one was segmentation. So this is a rough thresholding of an MRI scan, but then we can, using GIBBON, we can segment those MRI scans here to get, for instance, the tibia. You can see it's quite an irregular shape. And you can do this for all the bony surfaces and the skin surface as well. Next, we want to represent the mechanical properties. So we wrote some papers on this. I have my special flavor of an Ogden hyperelastic that I like people to use. That's for the constitutive behavior. Now at MIT at the time, they had developed this indenter system that I don't like. It looks extremely fancy. It looks like a large hadron collider, some kind of circular array of indenters, but they're square tipped with sharp edges and they all go at once. So when I arrived there, I was like, no, let's just use one at a time, turn all of them off. And can we not use spherical tipped, spherical headed indenters? But they didn't have that. But anyway, we did write a paper on that and quantify some mechanical properties using this method, but a different indenter system, a much simpler indenter system would be better actually. So there's some slides that people like and that I've shared on Twitter before as well, and that I've included here too about the Ogden formulation, right? So I tend to use a coupled second order Ogden form where I say that the first two C's are the same and the M's are also the same, but one is negative. So it's really, there's two parameters, a C and an M to figure out. And then if you rewrite the Ogden equation, you get something that looks like this. So you can see your positive M and your negative M. So why do I do that? So here's the normal Ogden form, and we should say plus something to do with the energy on the right, but there's different ways of implementing that, so I left that out. But you can see lambdas, the stretches, are to the power of M's. So that's the thing that puts up a resistance, right? So like when the strain is increased to these lambdas, the stretches go up, for instance, if it's a tensile strain. And to the power of M, that becomes something big, right? If it's to the power of 6 or to the power of 12. You can definitely see that as you apply a tension, these components go up and up and up. Another thing to note, though, if it's in compression, and this is, say, half, that's quite significant now, but let's say 0.7 for 30% compression. A half to the power of 6 becomes a smaller and smaller and smaller contribution, right? The higher you put M. So I found that a bit funny. If you use positive M's, you kind of crush compressive responses and you enhance tensile responses. So that's sort of the meaning of these parameters. So let's have another look at the anatomy of the Ogden formulation. So again, it's a bit difficult to see how this works. So you can pull this apart. You can explore the anatomy of the Ogden formulation a bit more. And we can see that there's a -3 there. So a stretch of an undeformed state is 1. So that's why there's a -3, because there's a -1, -1, -1. So if I write it, well, if I put a -1 there, you can see that this term will go to 0 in the initial state, right? And you can also do that for the other two. And then you can see, okay, this is clear. In the initial state, this is 1, -1, 0, 1, -1, 0, right? So now we have all this stuff. And we could put brackets around it to really see that there's 3 things happening there. But bear with me for a moment. We can vector out this 1 over MA as well in the front. Why would we do that? So we put it there. Meanwhile, we're thinking, why does it do that? Well, if you do that and then you multiply that, you work that into the equation like this, then you can see now, hopefully this looks a bit like a strain. For instance, the Green-Lagrange strain, if you just imagine M to be 2. So you have half lambda squared minus 1. And that's a Green-Lagrange strain. So now the Ogden, as you can see, features the sum of strain components. And these are principal strains, right? And in fact, this is the Seth-Hill class of strain tensors. Or these would be the principal Seth-Hill strains. And I think that's a nice way of looking at the Ogden formulation. You could see that depending on your M, you're picking a different flavor of strain. One that favors tensions, one that favors compressions, or something in between. And if you pick M equals 2, the Ogden formulation becomes Neo-Hookean, I suppose, if you have a single term. And if you pick M equals 2 and M equals minus 2, so a 2-term Ogden, you get a Mooney-Rivlin form. But yeah, so positive M's make basically the response in tension go to infinity. And negative ones make the response of compression go to infinity. But in between, they have funny behavior. If you only use a negative one, your tensile response has a maximum and just basically in the limit, just it doesn't keep going to infinity, it actually flatlines. Conversely, if you have only a positive M, you have a fine response in tension, but in compression, that strain would just bottom out and become, for instance, the Green-Lagrange, that is the red line, goes to minus half in compression at most. So when you squash a structure completely flat, it goes to minus a half. That mightn't be something that you want your strain metric to do. You might want it to go to minus infinity. So that's why these other strains came about. This has Seth-Hill class. But you could see that some favor tension, some compression. So I was like, why don't we do something with the two of them? Oh, sorry, I forgot that I first grouped this together and recognized that we could sum these 3 strain types together and use the summation symbol in there. And we could see that these are principal stretches. So the thing with the blue ellipse around it is actually a principal strain. And we are summing up over all 3 principal strains. Well, if you do that, that's actually a trace of a tensor. So we could write it the Ogden form even simpler like this. Say it's just C over MA times the trace of this special strain, which is the Seth-Hill strain. So there, that's a nice way of looking at an Ogden formulation. And why am I proposing positive and negative M's? Well, so this is from my paper on tension, compression, or symmetry in Ogden forms. The red springs is what happens. So the top row is tension. And so if you get a block and you pull at it, that's tension, and you pull it up, you extend it, uniaxial tension. Where if your M's are larger than 0, then you have a resistance in this red direction. Okay, it puts up a fight. And the other directions, they would shorten, right? If it's sort of incompressible, as you pull at it, it would get narrower and narrower in the other 2 directions. But those directions, they are shortened, and those, they don't contribute a lot, very little, in fact. The opposite is true when you have a negative M. Then when you compress it and you shorten that direction, those features really come into play. And if you use both the positive and negative, then basically compressions and tensions are specifically penalized by the terms in the Ogden form. So have a look at this if you're interested in it. I tend to think that if you don't know what the material is like, then if you use only a positive M, which means Neo-Hookean, Mooney-Rivlin, or first order Ogden with a positive M, then you're saying tension is most important in my material. But if you don't actually know this, then why don't we start symmetric and then use experimental data to say, well, actually, it's a bit asymmetric. In compression, it behaves like this, in tension, it behaves like this. But if you only do an indentation test, which is a bit of a mix of everything, then we don't have that experimental data to tease it out. So I start off symmetric. I tend to do that. But anyway, people can argue against that, but that's what I tend to do. All right, so one strain that I've introduced in the paper is to say, let's use a positive M, one strain like that, and one strain with the negative M, and use a Q factor here to kind of create a mixing. If you use Q equals a half, then your strain energy function will have this symmetry property, i.e. that a tensile strain will be equivalent of lambda 1 will be equivalent to a compressive strain defined by 1 over lambda 1. Okay, so that's the form that we use, and so that's the constitutive behavior. So that was a bit of a side note on the constitutive behavior of the soft tissue, but we could have equally well used any other formulation. Okay, so now next part is, so we have the geometry, we said, the surface geometry, we have some mechanical property information. Now we want to initiate a design. So I automated this based on landmarks. So you can see bony landmarks there. So G and F are the back of the condyles of the femur, for instance. B is the middle of the patella. And there's lots of landmarks like that. I can ray trace from the center along these points to the skin and create intermediate points that have sort of, say, that are, say, in between two of these points. So I can mix and match to create all sorts of points on the skin. And with that, I can define this curve. So, which passes under the patella and dips a bit below the condyles in the back. This is a typical cut line shape that you see in prosthetic sockets. So we use this to initiate the initial design. This is just thickened from the surface. And this is an unloaded surface from an MRI scan. So this is fully shape matching. So this is what we call a draft socket. It is shape matching and therefore a tearable socket, because it would be like a shoe that you don't feel when you have it on. As soon as you step into it, you're like, oh, this shoe is a bit too loose, right? So you shift and slide into it. You would like to tighten your laces in certain places, or like, you know, when you use your fingers to go across your shoe and tighten it more in different places. That's kind of what needs to happen with this socket still. This socket is just shape matching, so that's bad. So how do we alter the shape to get the best fit? And also, instead of rigid, maybe we need a material distribution, like some soft rubber in some places and some harder materials in other places. How do we figure that out? If you look at the literature, there's some information on vulnerable areas being reported. Like you don't want to create a hard material right at the patella, or right at the fibular head, or right at the tip of the fibula, or right at the distal end. Or you don't want to press hard there, right? You kind of want to avoid loading at those places. So these red regions are no-go zones, or at least you want to be careful there. The green areas that I've highlighted here are safer. So the calf in the back, quite safe. That can really take a beating, as I say here. But the other, so in summary, basically, stay away from bones. When bones are close, you want to stay away. When bones are far, it's safe. So this is actually sort of a bone distance map, but or at least it looks like a bone distance map on the skin. Red is far away. Now red is actually safe. I should have flipped this around. And blue is actually vulnerable. Another map that you can create, which looks very similar to a bone distance, is the tissue deformability. You can just create a model of your leg, subject it to a homogeneous pressure, and then see how it deforms. So if bone is close, the skin will stay put. It won't go in very far. If the bone is very far away, that deformation will go in. Like the pressure will make the deformation go in lots. And using the magnitude of the displacement on the skin, you get this map. And I was wondering, why don't I use this as some kind of initial guess of the fitting pressure? So I can use this scalar colored map to inform how hard I should press at the tissue. Okay, so the prosthetist does this with their hands. They squeeze the tissue and feel where the bones are, and they adjust the mold in that sense. So this kind of replaces that step of the prosthetist. And we can map this straight away to the socket design. So now we have, this is still a draft socket, but now we have sort of a design map, which we can use to distort it and morph it and change its shape. This should be the subject of optimization, by the way, but this is just an initial guess. So we use this map to define the local tightness of the fit and also possibly local stiffness. So if you have a very fancy 3D printer, like on the right, we could create a soft region over the shin bone, for instance, and at the fibular head, if you wanted to. Right, so how do we model donning of the liner and the socket? So a liner is kind of like a sock. So this master Jedi of putting on socks on the left, well, like I'm saying that because he seems to be really, that person seems to be really good at it. When I do it, sometimes I have to adjust where my big toe has to go. I'm not sure if you ever have that problem. It's like, oh damn, I put on my sock, but it's twisted. I have to do it again. Also, when you put on your shoe, I never put it on that smoothly. I tend to have to wiggle my foot a little bit to settle in my shoe. Maybe you recognize that, but that's exactly what people do when they don a socket. They do slide their leg into a socket, but they do wiggle and push, and they get it right. Like it's not a simple motion at all. So how on earth do we simulate this? So you could say, well, let's just slide them in, you know? Let's just create a 3D computational mechanics model, a finite element model, and solve a large nonlinear sliding contact problem with high friction. First, you have to put on a liner, which is the blue sock that you see on the right there. And then you have to slide it into the socket. Now I think nobody, if you know anything about FEA, I think you feel like this guy. You want to throw up. This is a terrible simulation that's going to take forever. Very sensitive to sliding. It's horrible. You want to avoid sliding like the plague, or contact as the plague, as I say to my students. So how do we do it then? We'd love to have sort of a magic plaster. What if we put on plaster which doesn't deform the skin yet? It's just sort of a draft socket that sits on the skin. And then we kind of want to take the prosthetist's hands, morph the design, and say, okay, now solidify. Because then it's sort of already on. We've already created a socket that's on. It's just neutrally on. So can we not deform it to be in the sort of the shape that we want? And the answer is yes. How? Now this will require a bit of explanation. Multi-generational materials. That sounds very fancy. This is actually a demo in GIBBON. This is a block, and the thing that looks green in the end is actually our multi-generational material. The thing that looks blue in the end, so when the cube comes back down, so when it comes back down, there, the blue material is a multi-generational material. That's called material 2. Unfortunately, it's the red line on the left. Okay, so initially, what we could do is create a space in our material, and we give it an initial stiffness that is basically worthless. It's nothing. It's ghostly. It's nearly zero stiffness, insignificant. The other side of the cube here has a normal, say, rubber-like property, and that's our blue line. It just stays the same stiffness the whole time. But at time number 1, which is sort of the end of the first generation, I'm going to say, well, in this space that is occupied by my multi-generational material, I'm just going to pour in my artificial magic plaster and have it solidify. But we solidify it critically in the deformed state. So we can pull up the cube, pour in a stress-free material, have it solidify, and then bring down the cube. And that's why that material in the end is stressed, and the other one is not. But anyway, this is a visualization of multi-generational materials. If this visualization is a bit complicated, just remember multi-generational materials, which are available in FEBio, allow you to deform a space and then say, okay, well, this deformed space is now a new reference configuration for a new material that I'm now just going to pour in. As if, say, soft cartilage turned into bone, and the newly deposited bone is stress-free, but the original cartilage did develop a stress. And you could have several materials sandwiched together that develop stiffness at later points. So I use this. This is, again, a difficult-looking simulation. We have the pink leg, and first I apply a fitting pressure for the liner. So with that pressure, I deform the leg, and I obtain the shape of my initial liner shape. I then initiate my liner design, and I relax that pressure, and the skin settles into the liner. Then I deform the outer surface of the liner with another fitting pressure to obtain the shape that I want for the socket. I then initialize the socket. This could be a socket that has locally rubbery-like materials. So then I let go of the pressures again, and the leg settles into a potentially compliant socket. If it was a rigid socket, nothing happens, right? It just pushes against the rigid wall. If it's a compliant socket, at that point, the tissue will settle into this compliant socket, right? So this is the process with multi-generational materials. I can create a ghost-like liner that I deform into a state that I wanted to have, solidify it, and then relax the tissue into it, and then deform a ghosted sort of zero stiffness socket into a state that I wanted to have, solidify it, and let the tissue relax into it. And then I've both done the socket and designed it at the same time. So it's donning and design in one go, right? So there's 5 steps: liner design, liner donning, socket design, socket donning. And the 5th step is I just press the socket upwards with body weight force, which is in this case a simple evaluation of standing in the socket. And then we look at the stresses and strains that have developed in the socket. If we like those stresses and strains, we can move on to 3D printing for manufacture. Here's a rigid socket, fully white nylon-like material, and that's ready for testing. So we did this on a subject. They came in with their prosthetist-made sockets, and they had to use crutches because it was too sore, and they could walk in a 3D printed socket. So that was super encouraging, and that's the initial work. We also equipped them with pressure or force sensors, very basic ones that I don't like, but we still needed to do some force measurements to show that at least compared to their normal sockets, we didn't make things worse. We made it better in quite a lot of places. And yeah, so this was encouraging. But this still without optimization. This was based on that distance mapping that I showed you. Nothing is optimized yet. So it's sort of already quasi-equivalent to what a prosthetist could do. But more work is needed. What is missing? MRI is too expensive. Indentation is too complex. That machine is too complex. True optimization is missing. This optimization loop currently not happening yet. Clinical evaluation and testing is also needed. We need to learn more about, is this initial guess quite good, or can we improve that type of guesswork? And also we need reliable force and pressure measurements of the sockets to evaluate it with those subjects. Which I think maybe somebody can point me to some, because I'm really looking for some proper pressure and force measurement techniques in the socket. So here's a novel solution that we're working on, or at least this is from the Matrix movie, right? But the novel technique that we're working on looks a lot like that. We have a ring of cameras around the leg, and Dana Salav developed this when she was at MIT. And basically we can speckle the leg with ink and do this full circle 3D imaging around the leg. So we can do bullet time visualizations, which in itself is just worth it doing it. But also this gives you the 3D shape of the leg, but critically, digital image correlation allows you to track deformations. So now we can do indentation testing and strain imaging as well in the same setup. So we developed sort of a gripper that can indent with a very expensive force sensor. Yeah, and then with that information, some force and some changes in shape, we can train again with inverse FEA a mechanical model. All this is very low cost. These are Raspberry Pi cameras that are $20 probably ago. So much better than MRI. Although you'll be missing bones. So can we also estimate bone locations? From MRI, we can just segment them. So here I developed a thing, a very simple method to guess bone locations from a pressure test. So this is an idea, actually, so I haven't done this yet. But these simulations I've done, but I haven't realized it with the device. What we would need is a pressure tank that goes around the leg, applies homogeneous pressure, the skin surface deforms, and I'm saying that it probably shrink wraps around the bones a tiny bit. So fluids are kind of squeezed out of that region, go up the leg, and the skin would deform a little bit. And if I manage to exaggerate that deformation further, I can actually predict the shape that's in there. So on the left is the true shape, sorry, and on the right is the predicted shape. And you can see it's actually surprisingly good. This really amazed me. I just thought this would never work, but it actually does for these deformations that you see. So the gray bag is deformed into that shape in the middle with a pressure field, and then I exaggerate it. But this needs to be tested. We need devices to maybe compress like a homogeneous pressure tank, and yeah, to use that to predict the bones. So that's something that I'm thinking about. So this other thing that was missing, optimization. Can we do topology optimization for sockets? Here's a bar with a force at the end, and topology optimization can be used to optimize its design. But the objective function, so it's sort of how good this design is on the design itself. And that's the problem for sockets. The objective is in the tissue. So it's sort of an objective at a distance problem, and that's much more complicated. So if anybody has any thoughts on that, I'd love to talk to them as well. And then this is also future work. We could incorporate lattice structures in the sockets as well. So to spatially vary the stiffness, not by switching to a rubber-like material with a very expensive printer, but to use more conventional printing techniques and then change the lattice structure type. I have some methods for that already in GIBBON that people can evaluate, but I'm still working on optimizing that, and also to have a spatial variation of it in a connected sense. So to go from a stiff lattice to a softer lattice in a continuous sense. All right. And I have a project that just started, and there's a postdoc and PhD position available if people are interested, to create novel open source solutions for prosthetic socket design, and that do feature topology optimization and these novel imaging solutions that we've seen. And we're going to test it in the clinic here in Ireland as well. So that's very exciting, and that's a project that's just starting called Simuling. So the framework B that you see here is the prosthetic socket framework. I've translated it into A, C, and D already, which are a foot ulcer prevention insole project, a face mask design project, and see there is a customized hip. So yeah, all of these problems are some image data, some geometry, some automated handling of a design, and some updating, but it's all mechanical interfaces. So if you're interested in those, let me know, and I can point you to them. You can likely find them already. This is another framework that I'm working on, not design in this case, but mammography evaluation and presenting the tumor location to the surgeon at the end, which is also using GIBBON. All right, so with that, I think I've spoken too long already. It's half an hour, but I can talk more about GIBBON if people want, but maybe it's a good point to answer questions at this point. And I'd like to thank my collaborators at MIT, Professor Hugh Herr and Dana Salav, who is now at the Technion in Israel, I believe. All right, maybe I'll answer questions first, but I'm more than happy to open some demos in GIBBON and to show people how that works as well. All right, thanks a lot.
Fantastic presentation. Thank you so much. If people have questions, please speak up. Manuel, are you unmuting with the question or?
Just getting ready, I guess, for conversation, but other people should go first.
I have a brief question while we're waiting. I think you tweeted the image that's on this slide saying that it was like a complicated but beautiful visualization. Could you talk us through it? Because I saw it the other day and I was curious.
It's actually, so I could go back. Do you remember the one where it was sort of pulsating as well, like sort of pink and then blue and then the socket in and out and out? It's the same. This is just, basically, I thought this looked beautiful, but it doesn't really help convey any scientific message. So I created it mainly for artistic purposes. But basically, this is that 5-step process. It's playing a bit too fast for me to talk in real time, but it's basically loading the liner, and the liner and socket are in a ghosted state still and being pulled along. And then the liner solidified and we relax into the liner. And then a new field is applied to kind of squeeze the socket into a shape that we want, and then solidified, and then we let go again. So that's why you see these sort of pulsating fields, kind of looks like a heartbeat almost. And then at the end, the lines go up because there's a displacement of the socket up as you stand into it. You load your leg into the socket. Is that explain it?
Yeah, thank you. Yeah, no, I'm trying to picture the like 5-step schematic pipeline in my head as you speak.
Yeah, it often takes me a long time to talk to people about it, but that is, I think, and I'd love to hear from other people that do contact simulations. It is the key trick to avoid the contact simulation. The only downside is that I don't model sliding in the socket. Right, so but it's both the key trick and maybe weakness, but I think it does make it much faster than contact simulation. I think these simulations take minutes, and you're probably into hours if you do a contact simulation. So for iterative optimization, this is much better, I think. Are there any other questions?
I see a question from Matthias.
Yeah, first of all, I have to say I really enjoyed all the gifts throughout. I was just wondering for the problem where you were looking at, can we learn the bone location from the deformation? Is there, do you have an idea of what pressures you would need to do that? And is that something that you can bear as an individual to have those pressures on there?
I should explore that because I'm not sure if what I've invented is not possible with physiological pressures. We do know that, I'm not sure if Dana Salav is on the call. I saw she did. Do you know this, Manuel? If she is, she can comment on the volume change of legs. But if you have a socket, we have one paper on it, so I should know the percentage. But I want to say at least 10%. But make sure you check that. So if you look on Google Scholar, my last name and Solav, and then volume change, there's some data on sockets. But this is if you stand in a socket for 10 minutes or 15 minutes, you're basically, the fluids leave that region and go up the leg. So we tend to say soft tissue is incompressible. Well, that's, I think the immediate response is incompressible. We're basically sort of a bag of fluids, right? If I hit my leg or my arm here, it's a bag of fluids, and water is incompressible. So it's, yes, the tissue is incompressible, but if I put a tight band, if I squeeze my arm really hard and hold on for a very long time, that tissue will sort of squeeze out fluids and it will locally change volume. So to answer your question, I don't yet know. This is really just a creative idea that I just had, and I thought I'd share it with you. It's not published, and I haven't evaluated the pressures yet. It could be that it's science fiction to do this in reality, but I'm also thinking about this study that we did, that it's in the order of, say, 10% volume change. Yeah, how wrong would it be based on such a small deformation to predict the internal shapes? It's better than not knowing the bone locations, but yeah, so this needs to be explored. I don't know yet.
Thanks.
I also had a question, Kevin.
Yeah.
So I thought, thank you very much. So I have 3 questions. The first one is when you showed the initial patient evaluation, and basically you showed us how you model the, so basically the constitutive material law with an Ogden one, but basically you use the passive response, which is different from the active response when you contract your muscles. And
yeah, definitely. Yeah.
How strong is this simplification, and how did you reach correct results without taking that into account?
Well, so I think I'm not claiming correct results. I think I've showed you that we use this basically this bone distance map almost to guess what a good field would be. And the boundary condition is that when I step into the socket, I didn't mention this, but I want to produce body force by sinking into the socket. I think it was 3 millimeters for these simulations. So that's called pistoning. So if you look at my, I'm not sure if you can see the camera, but like as you sit into a socket, like there's a pistoning happening, right? And that pistoning we limited at 3 millimeters. At that level, we should counter body weight. So that, why did I mention that again? That was a boundary condition, but will it matter if it's active? Yes, the muscle tissue is way stiffer, obviously, if it's contracted. But that is a difficulty too, because it's also very anisotropic, right?
Yes.
And these people, I'm not sure, actually on the picture on the left, you can see an ugly one. It's not ugly, but you can see a scar in the bottom of the residual limb, right? Do you see this at the number 3 on the left, on the limb? You can see a scar. That, if you feel that, on this subject, if you feel the calf, it's very soft. It's kind of like my cheek is soft, you know, that kind of stuff. And towards that scar, it becomes stiffer because it's a scar. So I think what you're getting at is much more realistic mechanical properties, right? Like active contractions of the muscle tissue, and maybe connective tissue and scarring tissue and all these places. And actually the scarring locations could be very sensitive too. So this distance map that I have should have extra vulnerable spots that are due to scarring or something. Now these are all easy to model, right? My simulation in FEBio does not go slower or significantly slower for me if I introduce fibers. Also not so much if I make them active. It's just that those parameters are experimentally not known, right? And that's the annoying thing. I was trying to make it cheaper by switching away from MRI, but MRI would give me, with the fusion tensor imaging, I suppose, the fiber directions as well, right? So we need to do a study where we, I suppose, put fibers in and that are very realistic and activate them and see, would that change the design decisions of the socket a huge amount? Or actually, does it not matter so much? Can you just get away with a single isotropic jelly-like material like I've done here?
So that was my, because I want the others to ask questions also, but I was wondering if basically at some point you could use the MRI in order to test how much your simplifications, typically how to evaluate the bone position from the external pressure that you apply, can validate your assumptions. And one of the things, so that was my second question, is typically you consider your soft tissue as one bulk isotropic homogeneous material. And I was wondering if typically you could use the MRI to validate the kinematics of the soft tissue and test the hypothesis of not including the fascia or not distinguishing the muscle from the fat, etc. And then say, okay, so I validated that it's fine enough and my decisions are robust enough, and therefore I can disregard the.
Yeah, that's possible too. Yeah, you can do a lot with MRI. I think studies like that are needed. So I'm looking for more funding to do work in this space, to do that sort of work. And yeah, one method also is elastography, right? You can do ultrasound or MRI elastography to estimate stiffness. So you can do quite a lot of stuff in the MRI scan. But I suppose it'll, yeah, for validation purposes, that's fine. I'm simultaneously thinking of a clinical solution where we don't want to use MRI, right? Or one that you know, this pressure tank system, if it would work, that could fit in a backpack and go into rural areas in Nepal or wherever in the world we need it locally, at very low cost. But yeah, for validation, I think we do need tests like what you described.
Yeah, okay, but thank you very much. Yeah, I'm going to stop here, and thank you very much.
Okay,
And
thanks.
we appreciated the GIF animation. It really made the presentation very lovely.
Great, thanks.
Thanks.
All right.
Yeah, definitely. It's sort of the most fun explanation of equations I've seen in a while. Did you want to show us a little bit of the GIBBON work?
Yeah,
or
if
yeah.
people, so I could show you first if there's no more other questions. I can show some other.
I had one question, Kevin.
Yep.
Hi, so I'm a PhD student at University of Illinois. Hi, everyone else as well. This is my first sort of attending a talk in this series. So I had a question. Have you explored the possibility of integrating physics-informed deep learning models, for instance, for inferring the bone shape using the pressure contour maps? So using neural net based, deep neural net based surrogate model. I'm curious to know how expensive is the simulation for that part. I mean, if it's even worth trying, because there have been some recent papers where the inference process, especially for these types of problems, has been largely accelerated using these surrogate type of models.
Yeah, I think so. And meanwhile, I'm running the framework of the foot. If people are watching what I'm doing, can you see my screen still or not?
Yeah.
Yes, we
so
can
I
see
think
it.
the simulation is running too in real time. So I think machine learning and deep learning, or all these different AI approaches, could be very beneficial to figuring out relationships that could work, because the prosthetist has this experience to palpate and feel the tissue and go like, yeah, I should stay away there and do this here and do that. It's very difficult for me to find a rule-based system that just where that pattern or that decision making evolves from the equations. That's very difficult at the moment, right? And I mentioned this optimization at a distance problem, and I'm not sure if people understood that, but if you do topology optimization with this truss that you saw with the force at the end, the local stress says like, I keep this element, no, I remove it. But if you have a socket that's on the outside, and pain and stresses and strains and tissue far away or at a distance inside of your body, right? Where on the socket do I need to make a decision to make that pain or that loading or that strain go away? That's a very difficult problem. It's yeah, I sometimes say it's like juggling 6 balls, 1 chainsaw, and a shark with laser beams attached to its head. It's a very difficult optimization problem. And I think maybe that's where machine learning could come in. Maybe we could scan like a ton of different sockets that have been made by very good prosthetists and see what the trick is there. Can we sort of infer the rules that they're using from that? Yeah. Do you agree that that could be where it could play a role?
Right, absolutely. I mean, that was what I was thinking. I mean, it shouldn't be completely curve fitting deep learning based approach, but rather sort of a hybrid between taking into account the physics of the problem and also leveraging the function approximation power of neural nets. So
yeah, no, I'd be interested in it. I have no experience yet with machine learning, but it is interesting. I kind of don't like it sometimes because it's a black box, but if it could push us in the right direction, then I think it's exciting.
Absolutely. Just one more question was, and I mean, it may offend some people, but was MATLAB a natural choice for you to sort of start developing GIBBON?
It's sort of unnatural in the sense that my PhD supervisor, when I did my PhD, was basically like, here, you should learn MATLAB. And I started using it, and I developed, we had no funding for something like simpleware for segmentation, or, you know, I had Abacus license issues that my colleagues were using up the Abacus licenses. And so I was like, okay, you know what, I'm just going to use FTBio. But anyway, MATLAB was kind of pushed onto me in that sense. And then I became too good at it to switch. So I'd love to switch to a language that is more open source, if that's what you're getting at. Like,
Right.
I think
Yeah.
Julia is a very exciting choice. If people are not familiar, you should look it up. Julia, the Julia programming language, is compiled, but looks on the outside of it very much like MATLAB. So as a MATLAB specialist, you can learn it relatively quickly, but get a huge performance enhancement, and it's open source. So that's something to consider. If I was a new PhD student, I would start learning either Python or Julia and try to use that. So I shouldn't say that because I want people to use GIBBON at the moment and collaborate with me, but I do think if I had to start over, I would do that.
How much of an effort do you see, like a complete overhaul of GIBBON into Julia?
How much of an effort it would be?
Yeah, I mean, how long has it been since you've been?
Oh, I've developed GIBBON since 2006, but not not as a job, right? As a, well, also I put anything in there that I find interesting. So it's sort of, you could say, it loosely stands for GIBBON, Geometry and Image-Based Bioengineering Add-on, but it really is like anything Kevin ever found interesting in his life. It's like a collection of methods that I found interesting and useful for my work, and it happens to be useful for other people as well. Yeah, so it's been a long time in the making. But if someone paid me for 3 months to just translate it into Julia, I could probably do it. But the problem is I'm not paid to do that. It's a side thing that I do. I teach and I do other research, and I'm supposed to write papers. So I can't afford to switch, if that makes sense. It's kind of weird. So CZI, the Chan Zuckerberg Initiative, is trying to fund open source developments, but I can't find funding to help you switch to open, if that makes sense. Yeah, it's a bit of a problem at the same time. Anyhow, I think this simulation just finished. Was there another question, or were you happy with that?
Oh, that was it at mine. Thank you so much.
Okay. So I just opened a demo. This is demo number 50, the foot insole. So it takes a leg. Here's a leg that I found on the internet. It's quite a bad leg, right? But it's just a demonstration. For demonstration purposes, you could replace this by a much better geometry. And then it contains foot bones that are, in this case, fused, but I effectively chop off the leg and fill it with the tetrahedral mesh in this case. And then what happens here? I take the points of the skin, and from the top of you, ray trace them down and grow them a bit. You can put a line around it to initiate a basic sole geometry. And then I run a simulation for that sole, which could be spatially varying stiffness. I think I show here sort of again a distance to the bone. So this could be sort of like blue is safe, red is unsafe. Same guess that you could make for the sockets is in here as well. And then the simulation itself, I'm not sure how long it took, but I think we were looking at it like minutes, right? So that's this whole code builds the design and evaluates it. Is there anything that people would like to see, or if there's more questions, I can address it. Oops, I was going to say as we're waiting and running another demo, but I think I'm still playing this. I should stop that.
Yeah, Kevin, I just wanted to chime in and thank you for being here today and giving this talk. I really, really enjoyed it. And I also want to say that it's really nice to actually, get to meet you sort of virtually. I've really enjoyed following you on Twitter, and my students are here, so hopefully I'm not saying anything that's not true, but I actually tell them to follow you and your work, because I think in many ways you're an excellent role model in that, you value open science and which I think is hopefully the future of our field. And I just also think you do excellent work, and I enjoy reading about your papers. I actually just recently read your Ogden paper from 2016 in quite a bit of detail. So after I saw that tweet of yours online, anyways, they say don't meet your heroes, but I can say that this time at least that wasn't
That's very kind.
So
very kind.
I really appreciate your work and want to encourage you to keep at it. Thank you very much for that.
Thanks a lot. That's very kind. So what I was showing here now, and it's nearly finished already, is basically it designed a subject-specific hip implant. So I take the femur, basically chop the head off, as you can see here. It's still running, so it's a bit slow at the moment. So it's running an actually biosimulation in the background. But basically, based on the bone contours, I developed this implant fully based on the subject. So there's nothing that I import here. The only engineering thing, I suppose, is the ball. I just made up a perfect sphere. Everything else is based on the subject and its orientation. And I think it's done evaluating it. And it took 43 seconds. You might argue that this isn't the best finite element model, but again, it's a a demonstration case, hopefully, for other people to build even better frameworks from. So here, I'm just putting a crazy force at the top. It's supposed to be body weight distributed by some muscles, but yeah, then it bends. And there's another simulation that could compare this to the non-implanted case, and you could optimize your implant maybe to have the same strain energy as the non-implanted case. Is there any other questions that I could answer? Otherwise, I can just keep running some demos and talk about them.
Yeah, I had a question, but I think you already answered it.
Okay.
I was going to ask what motivated each new addition to the GIBBON framework, but it seems that it's just whatever research topic you're most excited about. Is that more or less the story, or?
Yeah, and I very much believe that your work should feel like play, because then you enjoy it. So yes, it has been my scientific research, but also things that, somebody posted a tweet the other day about something called a squircle, which is a square circle. And there's an algorithm to go from a square to a circle in a really smooth sense. I have sort of this mental addiction that I then have to implement that. So I've implemented the squircle in GIBBON for no reason, but I'm sure I'll need it in the future. But actually, quite a lot of things that I use on a daily basis were in the past just a curiosity that I thought was fun and that are now very useful. I call that useful procrastination, and I encourage other people to do the same. Anyway, so probably half of GIBBON was for fun and the other half actual research.
That's awesome.
What you're seeing here is I use a triply periodic minimal surface called the gyroid, and I generated the FEA geometry, and I load it and I import the results. So it's always doing a finite element simulation in the background with FEBio. So let me quickly see if there's a picture here. So this is the GIBBON website, right? So if you want to figure it out, download it, go over there. See, here's an elephant foot that I segmented for no apparent reason, but it's very interesting. So you can loft stents and features, mixed meshing. This is what I wanted to show. So you might wonder, so can I show that image? Open image in new tab, right? If you're familiar with Abacus, or why can I not see that image? Is that readable or is that too small? Open image in new tab. Oh, here, it's here. I didn't switch to it. Yeah, is that readable? So on the top is how you'd code it in MATLAB. On the bottom is the input file for FEBio. So if you're an Abacus person, you should look on the right. But you can see I create a structure in MATLAB, say dot material number 1. Its name is Neo-Hookean. Its ID is 1. Its E, or Young's modulus, is 1. Poisson ratio 0.45. And you can see that that translates into this. So that's how things are coded in MATLAB with GIBBON. You code the top, and it creates the input file in the bottom and calls FEBio to solve it. Similarly, I actually have some demos for Abacus as well. So in Abacus, you'd say name elastic, and then the constants are 1 and 0.45. So these materials are sort of equivalent. So that's how you'd code models in MATLAB. And other than that, I would point people to my YouTube channel. I have an introduction to MATLAB there, and also to GIBBON itself. And I also want to encourage people to join, as I said, because if you contribute any code at all, I'm going to list you, or if you like, I list you as a contributor, and I would add you at the next as an author on the next GIBBON paper. And yeah, so hopefully that could give you some recognition, to say, as you're doing a PhD or a postdoc, to become a co-developer of GIBBON. And I'd like to give you as much credit for that work as possible. All right. Is there any more questions at this point? Things that I can highlight? Segmentation or meshing, or have we taken up too much time already?
No, you haven't. But I have one random thought about your sort of bone identification through inverse FE modeling, where you said you need to do it under pressure. I'm sure you've used these like Dyson fans to like dry your hands. Have you ever seen how they indent your skin locally?
Oh yeah, actually.
So I wonder whether you could like implement sort of like an air pressure mechanism where it's sort of like draw the leg through, or have it like scan your leg down. And combining that with your 3D DIC. Right.
And actually, we put this
maybe
in
that would be cool.
MIT. At MIT, I had a colleague who was in the workshop, like blowing away, like sawdust or whatever from a bench, like with this sort of gun-like thing. And he pointed at his skin and created a really nice indentation. If you get it wrong, it starts to like oscillate rapidly.
Right. But I wonder if you did it like 3-dimensionally, you know, like fan, and then you could sort of like
Yeah.
scan up and down and combine that with your
Oh, yeah.
DIC.
Yeah, but then you need the higher pressure, right? If you do this local tip, it's very low pressure, I suppose. And then you could solve a model such, the bones need to be such that it would predict the same deformation for all of that stuff. And the nice thing is you can see through the air, right? You can see the full deformation. Your indenter isn't in the way. So
yes, you would have to shave your legs, but
yeah, and you have to bring an
sacrifices.
8-bar compressor or like whatever pressure compressor up.
And then you can do like a whole body, you know, scanner where it's just sort of like, anyways.
With
That would
violent wind conditions, yeah, that would be very interesting. Yeah, that would be interesting. So
Yeah, well, oh, I was gonna say we're just at the hour, so I'll thank you one more time on the record and
All right.
stop the recording.
Okay,
Yeah.
that's fine.
But
Yep.